All right, let's just cut to the chase. Have you ever wondered what really separates a senior engineer from everyone else on the team? I'll give you a hint. It has absolutely nothing to do with writing the cleverest algorithms. Whether you're wrangling massive Kubernetes clusters or building out serverless architectures with AWS Lambda, making that leap from junior to senior is really about one thing. It's about surviving the absolute chaos of production.
And that brings us to this beautiful truth. Senior developers don't write better code, they delete more of it. I call this the deletion paradox. It's kind of wild when you first realize it, but your ultimate value as a developer actually becomes inversely proportional to the amount of code you write. Seriously.
Think about the contrast here. A junior developer joins a team, right? And they want to prove themselves. So they add 50,000 lines of code. They build these massive mountain peaks of new features. But what they're actually building is hidden cognitive load. A senior developer, on the other hand, they create valleys. They'll step in, delete 15,000 lines, rip out 3 microservices nobody even uses anymore, and slash redundant dependencies. Because at the end of the day, less code literally means fewer bugs.
So here's our roadmap for this explainer. We're going to hit the deletion paradox, obsessing over the tail, mastering the orchestrator, state and contracts, and finally, the human bottleneck. Let's dive in. All right, section 1, the deletion paradox. The core idea here is that your code is actually a liability. You really have to consider the brutal long-term cost of code. Look, human memory can hold about 7 pieces of information at once, but modern code bases, they have like 700,000. It's overwhelming. And then there's the 10x rule. Every single line you write is going to be read 10 times, modified 3 times, and debugged twice. That is a massive tax. Reducing that cognitive load for your team is infinitely more valuable than adding some just-in-case feature. Unused code isn't just sitting there harmlessly, it's active harm. It creates false complexity. So say it with me. The absolute best code is the code that simply doesn't exist. Moving on to section 2, obsessing over the tail. Let's talk about the unforgiving physics of the network. P99. If you are celebrating your median latency, your P50, I gotta be honest, that's a distinctly junior move. True professionals, we obsess over the P99, that 99th percentile, and we obsess over timeouts. Why? Because when you're working with hyperscale distributed systems, rare slow events aren't actually rare anymore. At scale, a 1 in a million glitch becomes your everyday reality. To put that into perspective, at hyperscale, a single user click can easily traverse 500 discrete microservices. It can trigger over 30,000 remote procedure calls, or RPCs. We see exactly this kind of massive web in Uber's architecture, for example. When your network path is that incredibly deep, a tiny, seemingly harmless latency blip in one random, non-critical service can easily cascade and take down the entire system. It's like a domino effect. So how do we actually fight back against that? Well, senior engineers use some pretty advanced mitigation tactics. First up, request hedging. This is where you literally issue a second request if the first one exceeds a P95 timeout, and you just serve whichever one comes back first. Then you've got pervasive deadlines. You have to propagate end-to-end time budgets across your services to stop those sequential timeout waterfalls from ruining your day. And finally, off-CPU analysis. This is where you go hunting for hidden wait times, things like locks, I/O bottlenecks, or scheduler delays. Managing tail latency means you have to engineer the entire request path to stay predictable, even when parts of it are failing. Okay, section 3, mastering the orchestrator. Welcome to the terrifying reality of DevOps. Let's walk through a classic, painfully real scenario, the scaling lag incident. Step 1. Your marketing team pushes a notification to 5 million users all at once. Step 2. Boom. Your existing pods instantly peg at 100% CPU. Step 3, your horizontal pod autoscaler kicks in, but it lags. It scales up, but it's 3 minutes too late. Step 4, millions of potential customers just got 503 service unavailable errors. Default Kubernetes scaling might technically win the metric eventually, but it completely loses the race against time. And do you know what the root cause of that failure actually is? CPU is a lagging indicator. Read that again. By the time your CPU metrics spike to 100%, the damage is already done. Your latency is terrible, and your users are already frustrated. A senior engineer knows you have to scale preemptively. You scale on forward-looking metrics like concurrent in-flight requests, or you artificially pre-warm your capacity right before that marketing push even hits. You really have to respect the brutal financial and architectural realities of your orchestrator. Take the bin packing trade-off.
Sure, you can guarantee quality of service resources to stop your apps from crashing due to out-of-memory kills, but you are likely wasting millions of dollars in stranded RAM to do it. Then there's the fsync speed test. Listen, if your underlying storage latency, like an etcd fdatasync, exceeds 10 milliseconds, your entire cluster is basically a ticking time bomb. And beware the hot pod trap. You cannot solve a massive 30-second API call just by throwing it at a load balancer. You absolutely must offload that to an asynchronous message broker. If you don't understand and respect the underlying Linux kernel and storage constraints, you aren't engineering, you're just renting compute.
All right, moving to Section 4, State, Caches, and Contracts. Remember this, compute is ephemeral, but data is forever.
Senior engineers are constantly playing this game of tug-of-war, weighing protocol efficiency against performance costs. For example, moving away from verbose REST and JSON APIs to gRPC over HTTP/2 multiplexing. That heavily reduces your network tax and drops latency. It's incredibly efficient. But then look at caching. A write-through cache is great because it ensures strong consistency, syncing updates to the database and the cache at the same time. The trade-off, though, significantly slower write latency. Engineering is just a constant series of these balancing acts. But what happens when your stateful data goes horribly wrong? Enter the stateful split brain. Imagine a scenario where a zombie pod corrupts the strict at-most-1 execution guarantee of your stateful set. This is a literal nightmare. A forced deletion causes your database replicas to silently diverge. Suddenly, half your users are seeing brand new data, the other half are seeing horribly stale data, and cluster consensus is completely shattered. It's a mess.
And hey, it's not just the databases that bite you, it's how all your services talk to each other. Have you ever seen a silent contract break? That's where simply renaming one tiny JSON field in a backend service ends up crashing 100% of your Android clients in the wild. Boom, down. This is exactly why we rely on the permissive parser rule. You have to build robust clients that don't panic over missing fields and keep your servers conservative in what they send. Oh, and one more golden rule. Idle in transaction. Never, ever perform a network call inside a database transaction block. You will lock up your connections and silently strangle your performance at scale.
Which brings us to our final section, number 5, the human bottleneck. Because the hardest problems in software engineering aren't technical bugs, they're human.
It's a fascinating fact, backed by research. Operator errors are actually the primary cause of service failures. And surprisingly enough, service front ends generally cause way more production problems than backends do. Despite all our fancy redundancy, automated failovers, and custom software, the human element remains the absolute most difficult failure point to mask. You can always spot the junior instinct. It's called the scream test. You know, shutting down a mysterious black box server and just waiting around to see who complains. Do not do this. That is a career-ending move in a large organization. The senior approach is entirely different. It relies on network telemetry. Before a senior engineer touches a single server, they use Cloudflow logs to build a mathematically perfect dependency graph. They establish absolute 100% visibility before taking action. Because when you guess in production, things go horribly wrong. Just look at these silent organizational killers. The environment bleed. This is when some leaky automation script from your staging pipeline accidentally targets and completely nukes your production environment. Then you've got the bus factor of 1, where a critical legacy system is locked entirely behind the tribal knowledge of one employee who happens to be on vacation. And of course, the read me first rule. You absolutely must write the on-call runbook before you write the code. Seriously, if your infrastructure isn't defined in Git as code, it simply does not exist as far as the team is concerned.
So, let's get practical. Here is a 5-step action plan you can use to stabilize your own systems next week. Step 1. Instrument end-to-end latency budgets across your stack. Step 2. Use distributed tracing to find your top 3 P99 latency contributors. Step 3. Go in and remove those avoidable network hops, fix the chatty API calls, and maybe switch to compact binary formats like gRPC. Step 4. Add explicit tail controls, like pervasive deadlines. And finally, Step 5. Make sure you can isolate failures and load shed traffic before you even attempt to scale your infrastructure up.
Which leaves us with one final provocative question. What code can you delete today? I really want to challenge you to apply this senior mindset immediately. Stop trying to build these complex, massive monuments of code to prove your worth. Start ruthlessly optimizing, simplifying, and deleting. Because in distributed systems, less is always more.
Thanks so much for joining this explainer, and I'll catch you in the next one.